Hello and good morning. Welcome to my data center technical series. This is volume 1. My name is Anthony Rogers. Seeing as today I'm officially an electrical engineer. I just graduated with my master's degree in electrical engineering from the University of Washington. I'm so excited. I figured I would start my data center technical series in reviewing all different types of areas of focus for me, and I want to share and empower you with this information. I see a lot of different individuals out there who are interested in this technology. They just don't have any avenues to go out and peruse it or apply it effectively. So what we're going to look at here first today, and I just drew up this little circuit, is the importance of divider circuits and monitoring systems all throughout data center and critical infrastructure. Now, divider circuits are very, very important depending on the analog to digital converter. Now, new type ADC systems will have 16 to 24-bit analog to digital converters. The reason that's important is because they'll have a max ceiling on the digital bits input that they can have. For example, if you have a 540 volt DC bus and you're trying to scale it all the way down and you have a 12-bit analog to digital converter, you only have 4,096 counts or 4.0096 volts to scale it into. So you have to scale it way, way, way down, and that's what the importance of these divider circuitry, which is what you actually see here. So the divider circuitry, what this is going to do is you'll have an input there, which is two 30.1K resistors. We're going to add those up. That'll be 60.2 K ohms. We're going to divide that by the total resistance in this entire circuit. And you can see above that there's actually two 10K resistors and also two 90.9K resistors. So the entire resistance of that input circuit, now this is for a 12-volt monoblock on a battery monitoring system, is 262,000 K ohms, or 262K. So we take the input, 60.2 K ohms, divided by 262 K ohms, and we get a multiplier. This multiplier is 22.9%, or 0.229. You take that input and you multiply it times the input voltage, because we have two 10K current limiting resistors out there. They're also part of that divider circuitry. And what you're going to get is a representation in voltage feeding into the analog digital converter. So you can see an operational amplifier there. I'm going to have another series on op amps, so I'm not going to go too much into that now, but that's going to basically pass that voltage of 3.03 volts directly into the ADD, and that multiplies it by 1,000, and you get a digital representation of 3033 or 3,000 analog to digital counts. Now, it's very important to understand what this is doing and why it's doing it, because when we're troubleshooting monitoring circuits, if you don't understand the very basic premise of input divider circuitries and how each system is either limited or enhanced by their inherent design characteristics, you can miss quite a few things. I'll give you an example. Let's say we go to a facility that has 242-volt wet cell batteries, and these 10K current limiting resistors are sitting on top of the battery system. And let's say some of the acid eats through that butt splice, and now that 10K resistance has gone up to 20K or 30K. Well, how does that impact the monitoring system? What you're going to see is a voltage drop across that connection, and the system will basically shift up like this. Now, I'll put an image of that up here if I can find one from one of our technical reports. I'm going to dive into this in detail in an Excel spreadsheet that I designed for you to help you understand why this is important. And again, I'm going to touch a little bit on op amps later, but those op amps are fed, most op amp operational amplifiers are fed by rails of 5 volts, negative 5 volts to plus 5 volts, and that essentially is giving it a full-scale resolution. So if it loses one of those power supplies, or if a capacitor shorts, the op amp will short, and the input will go to rail or will go high. You'll have a maximum input of 4,096 volts. This may seem difficult, and I'm going to step you guys through this, but just try to remember that what we're doing is scaling inputs down. So if we have a 12-bit analog to digital converter, we have to scale everything down to less than 4.096 volts. If we have a 16-bit analog to digital converter, generally you can scale from 0 to 20 volts. Now, what this is doing is increasing your resolution, right? So if you have an input signal and you have to scale it way down, you're reducing your resolution, especially when it's inherently input into your calibration constant. So you must absolutely understand the scaling factor within analog to digital circuitry. So when you're designing new systems and microprocessors, we want to choose a higher quality ADD, like a 24-bit ADD, 16 to 24-bit ADD, so we do not have to scale so much in regards to some of these systems, because it creates quite a bit of troubleshooting headaches down the road when you're troubleshooting something 15 years old and it has this antiquated circuitry and you don't quite understand. This is why divider circuitries are so important, and you have to understand it. So what it's doing is scaling that down. So let's just review it very quickly. The input divider resistance. So if it's 30.1K and you're going to add those two together, you can kind of see that right there. Those two resistances is the divider input. So we just add those together. 30.1 plus 30.1 equals 60.2 divided by the total resistance in the entire circuit. That means all the 10K current limiting resistors out at the battery system, and then we have we have some inductors here, some filtration mechanisms, and then we have another 90.1, 90.9K. We add those two together, everything together, and then essentially we're going to get a multiplier from that, and we multiply it by the input. Awesome. So let's jump into the Excel portion of this. Just a 12-volt monoblock first, and then I'm going to spread it out into all right, we're back. So what we're looking at here is a raw analog to digital count multiplier spreadsheet that I designed, going all the way down to the electrical schematics and looking at all the different characteristics of the entire system. So what you're going to see here on the left-hand side, this is a voltage scale, okay? So on this system, we have a 12-volt scale, and the DMM, our digital multimeter, is inputting and measuring 13.5 volts. And what you're going to see here is that multiplier, right? 229 or 22.9%. We're multiplying it by 1,000, which is why you see that there, because we want the digital representation and analog to digital counts. But now look, and when we change this, let's go down to 13.1 volts. And see how that changes on the input there? You're actually it'll have the low and high side, but we use this to calibrate the system. So if the system is, if there's a high resistance on the input, you're going to incorrectly calibrate it. You're not going to have enough room on the top end of that ceiling for the system to move up and down. So that'll mean as it moves up the voltage, it'll get scaled. It'll get maxed out. So this is very, very vital to understand within monitoring circuits, because if you don't apply some of these fundamental principles to the multiplication factor and the divider circuitry, the analog to digital circuitry, you'll have no idea how to troubleshoot these monitoring circuits effectively. Okay, so now let's jump into a full scale system where you have 2 volts, 4 volts, 6 volts, 8 volts, 12 volts, and you can see all the different multiplier circuits that we apply in different monitoring around the world. Let's go. All right, and welcome back. So what you're going to see here is this full system circuit analysis in Excel, and what I have is a calibration factor times the ADD counts will give you that measured estimated input. Okay, that's kind of like the reverse if you want to double check your work. But here on the scaling here on the left hand side, you'll see the scale voltage: 2 volts, 4 volts, 6 volts, 8 volts, and 12 volts. And then we have different readings, but then we'll have the multiplication factors. And I actually split some of this out here for the multiplication factors that you can see. Each one of the systems, as you can see, on the 2 volt scale is actually the highest resolution. Why? Because we don't have to scale it down so much, right? We have a 4096 count ceiling, or on a 16 volt system that's 20 volts, or 16-bit system. If we had that, we wouldn't have to scale it, but because some of these older monitoring systems, actually it's quite common across the entire industry. It saves cost, right, on the building materials, but on this, it doesn't have to scale. So on lower input signals, you're going to have a higher resolution. As you increase the voltage, you're going to have a lower resolution. And then you're going to see that across all Fluke Spectrum products, all monitoring systems, all power quality systems. It's the same exact thing. This applies to every single monitoring circuit you're ever going to see. That's why it's so critically important that you understand these basic fundamental principles. Okay, so, and what I showed you earlier with the multiplication value is exactly the same here. And if you want to work it back, once you have all those values for your nominal, analog, to digital counts, we work that back by taking the calibration constant, or that factor, which we won't get, and we multiply it times the input A to D counts, and that gives us back our measured input, which is V equals R times K. The K is a constant. So I hope you guys understood some of these basic principles. Again, this data center technical series, we'll be reviewing all kinds of different products from breakers, shunt trip mechanisms, capacitors, the importance of power supplies, microprocessor systems, internal resistance, conductance, impedance, and DC resistance. We're looking at transformers, inverters, rectifiers, IGBTs and SCRs, generators, switchgear, protective relays, needle level testing and IEEE standards and PA 70E. This is going to be far-reaching, and I'm so excited to be bringing it to you guys now that I'm finally an official electrical engineer. And I hope so the basic premise of this kind of gets through to you. I know it seems a little difficult to comprehend because if you have never worked on some of these systems, all you see is a bunch of numbers and values. But just understand that the divider circuitry is taking an input and scaling it down so we can fit it through a window. And that window needs to have enough buffer on the top and a buffer underneath so it can move appropriately within that input variable so it doesn't hit a ceiling and then essentially it's like first in, first out with a water glass, like on a memory overflow. You won't be able to see the high end if the voltage goes over 13.4. You would never see it because you miscalibrated it incorrectly. This is why it's so important that every single monitoring system has an annual recalibration. It's difficult for me to comprehend and fathom that all of these data center managers treat UPS systems so critically, but the battery monitoring system is literally monitoring the heart of the power system. Without the battery, the UPS is a glorified power conditioner. It's almost worthless, right? So all the monitoring systems should receive much more attention than they currently receive. And in my opinion, they should have monthly and quarterly and semi-annual and annual inspections and calibrations and verifications, because this system is essentially ensuring that the heart, the core of your power system that is ensuring you don't have a 10, 20, 30, 40, $50 million outage, the core of your system that is ensuring you have enough critical load protection time for the generator or your backup flywheels or your diesel rotary UPS to spin up and protect your critical load is, within operational manufacturer specifications. If you don't double check these things, it only takes one battery. The battery system is only as strong as its weakest link. Even in a series system of 40 batteries, you have one battery, battery 12, battery 1, battery 37, battery 40, it doesn't matter. The entire load will go to zero. In a parallel system, it's a little bit different because if you have a battery failure in string 3 on cell 22, a lot of the string current from the discharge will flow into that battery, and that can cause something we talk about as thermal runaway. There's an international fire code 608.3 that talks about tripping mechanisms for thermal runaway. I will have an entire video reviewing how to mitigate thermal runaway and the implementations on certain electrical design and mechanical switches and normally closed, normally open types of methodologies that you can integrate effectively to mitigate this entirely. So there's so many exciting things that I'll be discussing in future iterations of this data center technical series, but I want to thank you so much for tuning in to Volume 1. It means the world to me. Always reach out to me if you have any questions. Have a great day.